Hello all, this is a briefing of our final year project, Brain Tumor Segmentation using Encoder-Decoder Architecture. The team members are Alen, Antony, Fathima, Sadheeda and myself, Harsha, Anil, Kumar. We were guided by Professor Anitha Edison of the Electronics and Communication Department at College of Engineering, Trivandrum. Our aim was to develop a deep learning model to perform segmentation of tumors in MRI images. Over 1 million cases of brain tumors are reported in India every year. The most common type of primary brain tumors are gliomas, which arise from brain glial cells. Gliomas can be of low grade and high grade subtypes, with the latter being more aggressive. MRI imaging provides detailed images of the brain and is one of the most common tests used to diagnose brain tumors. Manual delineation practices require anatomical knowledge, are expensive, time consuming, and can be inaccurate due to human error. Automated segmentation of 3D brain tumors can save physicians time and provide an accurate, reproducible solution for further tumor analysis and monitoring. Our final year project uses autoencoder architecture for segmentation of brain tumors. This is the basic outline for our project. We have used MRI images from the Bratz 2018 dataset as our input. These images have been pre-processed using various techniques and fed into an encoder-decoder model, which gives the segmented output. Bratz is a brain tumor segmentation challenge that is held every year. The aim of the challenge is to evaluate the state of the art methods for segmentation of brain tumors in multimodal magnetic resonance imaging or MRI scans. The 2018 challenge utilizes preoperative MRI scans to segment intrinsically heterogeneous brain tumors called gliomas. The Bratz 2018 dataset consists of multi-institutional routine clinically acquired MRI scans of glioblastoma and lower grade glioma with confirmed diagnosis. These are provided as the training, validation, and testing data. All Bratz multimodal scans are available as Nifty files and describe four types of scans named native, that is T1, post contrast T1 weighted, that is T1C or T1GD, T2 weighted, that's T2, and T2 fluid attenuated inversion recovery, that is FLAIR. We have 285 cases, of which 210 are HGG and 75 are LGG. These are in total, out of which 228 have been used for training and 51 for testing. Here is how we have visualized the input for our project. That is the segmented output. We have used several pre-processing methods, which are N4ITK, mean, median, and Gaussian filters. The mean filter replaces every pixel in the image with the average of its neighbors and itself. The median filter takes the median of every value surrounding the pixel and replaces it with that value. The Gaussian filter, also known as the Gaussian blur, uses a function named the Gaussian function to blur the image and create a smoothing effect. The bias field, which is also known as intensity inhomogeneity, is a low frequency, spatially varying MRI artifact causing a smooth signal intensity variation within the brain tissue. The performance and quality of MRI images vary considerably in the presence of a bias field. The N4ITK algorithm is a bias field correction algorithm used for correcting low frequency signals known as bias or gain field, which causes intensity non uniformity present in MRI image data. It is a variant of the non parametric non uniform intensity normalization N3 algorithm, which is also used for bias field correction. Our segmentation approach follows an encoder-decoder based CNN architecture. The encoder part uses ResNet blocks, where each block consists of two convolutions with normalization and ReLU. For normalization, we use group normalization, which shows better performance than batch normalization when batch size is small. Here, the batch size is 1. So we follow a common CNN approach to progressively downsize image dimensions by 2 and simultaneously increase feature size by 2. For downsizing, we use strided convolutions. All convolutions are 3 by 3 by 3 with the initial number of filters equal to 32. The encoder endpoint has size 256 by 20 by 24 by 16 and is 8 times spatially smaller than the input image. We decided against further downsizing to preserve more spatial content. The decoder structure is similar to the encoder one, but with a single block per each spatial level. Each decoder level begins with upsizing, reducing the number of features by a factor of 2 and doubling the spatial dimension using 3D bilinear upsampling. This is followed by an addition of encoder output of the equivalent spatial level. The end of the decoder has the same spatial size as the original image and the number of features equal to the initial input feature size, followed by 1 by 1 by 1 convolution into 3 channels and a sigmoid function. Starting from the encoder endpoint output, we first reduce the input to a low dimensional space of 256, 128 to represent mean and 128 to represent standard deviation. Then, a sample is drawn from the Gaussian distribution with the given mean and standard and reconstructed into the input image dimensions following the same architecture as the decoder. The only difference is that we don't use this interlevel skip connections from the encoder here. We have implemented the architecture using a neural network in Python. Parallel processing has to be used to implement the N4ITK algorithm using CUDA in GPU. We've used Google Colab as our IDE. These are the training and validation scores obtained from the model. We use dice coefficient and intersection over union as the evaluation metrics. There are two parts in the output, the encoder output and the autoencoder output. Loss curves provide a mathematical representation of the learning process that takes place as task repetition occurs. Here are the loss curves obtained for both. Dice coefficient is essentially a measure of overlap between two samples. This measure ranges from 0 to 1, where a dice coefficient of 1 denotes perfect incomplete overlap. Here are the dice coefficient curves. We have compared the results obtained here with those of the unit architecture. Our model shows a significantly better performance. Thank you for watching.